Thank you for coming to my talk concerning properties at saddle points, a typical topic considered in Calculus 3. At a saddle point, like the canonical Pringles potato chip, the direction in purple and the direction in green are orthogonal. The direction in purple denotes the direction of maximal upward concavity, while the direction in green denotes the direction of maximal downward concavity. More precisely, that the second directional derivative of f in the direction of u is greater than 0 in the purple direction, but is less than 0 in the green direction. This is a theorem that typically requires a fair amount of linear algebra to prove, more precisely that the eigenvectors of different eigenvalues of a real symmetric matrix like the Hessian are orthogonal. And because that this requires a fair amount of linear algebra, that's my guess as to why this theorem isn't typically even stated in calculus textbooks, at least in my experience, let alone proven in calculus textbooks. And that's what I'd like to address with this talk. On screen is the typical second partial derivative test as it appears in textbooks. Let x naught, y naught be a critical point of f, and let a be the second partial derivative of f with respect to x, let b be the mixed partial derivative, and c is the second partial derivative with respect to y, all evaluated at the critical point. Then if ac minus b squared is greater than 0 and a is greater than 0, then x naught, y naught is a local minimum. If ac minus b squared is greater than 0, but a is less than 0, then we have a local maximum. If ac minus b squared is less than 0, then the critical point is a saddle point, and the test is inconclusive if a squared minus b squared is equal to 0. What follows is a typical proof that appears in textbooks, at least the textbooks which provide a proof of this theorem. And the usual proof of this theorem involves the directional derivative and the second directional derivative in the direction of u. So suppose u is a unit vector hk, then the directional derivative of f in the direction u is the gradient of f dot u. So h times the partial derivative of f with respect to x plus k times the partial derivative of f with respect to y. Then if we take the second directional derivative in the direction of u, we end up with h squared times the second partial derivative of f with respect to x plus 2hk times the mixed partial derivative plus k squared times the partial second derivative of f with respect to y. And then plugging in at the critical point, we get this key expression ah squared plus 2bhk plus ck squared. And we're going to be using this expression throughout the rest of the talk. So this expression in orange. The main idea of the proof as found in textbooks is to determine where this expression in orange is either always positive, always negative, or neither. And we do this by completing the square. And by completing the square and by taking a look at the expressions in red and in blue. Case 1a. Suppose that the red expression a squared minus b squared is always positive, and suppose that the blue a is also positive. Then everything's positive, and we're guaranteed that the second directional derivative in the direction of u is guaranteed greater than 0 for all h and k. By the usual second derivative test from Calculus 1, that means that x naught, y naught must be a local minimum at this in every direction, and therefore x naught, y naught must be a local minimum of f. Case 1b, suppose that the term in red is positive, but the a in blue is negative. Then we end up with a negative times a positive, and the net effect is that the second directional derivative in the direction of u must therefore be negative. Once again, by the second derivative test, that means that x naught, y naught must be a local maximum, and therefore f has a local maximum at x naught, y naught. The saddle point case requires a little bit more care. Suppose that h is equal to negative b times k over a. Then the term in purple is equal to 0, and so therefore the expression in the parentheses is going to be a positive times a negative, and therefore must be negative. On the other hand, suppose I take a different direction where h is much larger than k. Then if I have k is small and h is large, then I'm going to get a large positive times a negative, and the result inside the parentheses will be positive. Now you notice at this point I'm a little bit hand wavy on the argument, and this matches what typically appears when textbooks attempt to prove this theorem. What you see on screen is a picture from a textbook. If it's less than 0, then there are combinations of arbitrarily small non-zero values of h and k for which the expression is greater than 0, and others for which it's less than 0. not exactly convincing as to which values of h and k they are. So it's hand wavy at this point in the argument. In any event, we conclude that the second directional derivative in the direction of u, it could be either positive or negative, depending on which direction u is chosen. And so we conclude that we have a saddle point. And so that's the typical proof that's found in textbooks. A twist that I'd like to offer, and perhaps a new twist, is to instead write the directional derivative using the angle theta. So let's write the unit vector as cosine theta sine theta, and I have this new expression for the second directional derivative in the direction of u. We now apply trig identities. I'll use the power reduction identities for sine squared theta and cosine squared theta, and I also will use the double angle identity for sine of 2 theta. Next, let's collect the things that are trigonometric and not trigonometric, and so I get this new expression. Then for the term in gold, I notice that the angle 2 theta is common to both terms. And so therefore from trig, I can combine these into a single trigonometric expression. Now this might be a little rusty. And so in the gray, I put the kind of the logic for behind why this works. I'll choose a point where x is equal to a minus c over 2 and b is equal to the y coordinate. Phi will be the angle in standard position. And so this works out that I can use the difference identity for cosine to combine these into a single expression. The practical upshot is that the second derivative of f in the direction of u now is a trigonometric expression, where I have a vertical shift that's represented in red, I have an amplitude that's represented in blue, there's a phase shift, and also I see that the period of this function is equal to 2 pi over 2, which is equal to pi. That'll become important later. The main idea is that I need to again determine where is this positive? Always. Where is it negative? Always. And under what conditions is it neither always positive nor always negative? And this can be determined by looking at the relative magnitudes of the term in red and the term in blue. Case 1. Suppose that AC minus B squared is greater than 0. Then it's straightforward to show that the term underneath the blue square root is equal to the red term squared minus the green term AC minus B squared. So the green term is positive, which means that if I take it away, I make the right-hand side bigger, and therefore the amplitude of the cosine function is less in magnitude than the magnitude of the phase shift. So case 1a, suppose that AC minus B squared is greater than 0, and suppose also that A is greater than 0. With a little bit of algebra, we see that C also has to be greater than 0, and therefore the term in red must be positive. And not only is it positive, but it is bigger in magnitude than the amplitude of the trig function. So if I take a look at the graph, that means the graph must always be above the theta axis. The vertical shift is bigger than the amplitude. And therefore, the second directional derivative in the direction of u must always be positive. And therefore, it's a local minimum. Case 1b, suppose AC minus B squared is greater than 0, but this time A is less than 0. Again, by a little algebra, we see that C has to be less than 0. And so I conclude that the term in red is negative, but its magnitude is still bigger than the amplitude of the cosine function. And so if we're to graph this, the graph will always be below the theta axis, will always be negative, and for every angle, and therefore we conclude that the critical point must be a local maximum. For case 2, by the same reasoning, that the amplitude in blue must be greater in magnitude than the vertical shift. And because the amplitude is bigger in magnitude than the vertical shift, then we see that there must be some angles where it's positive, denoted in purple, and other angles where it's negative. And so no hand waving, we see definitely it must be sometimes positive, sometimes negative, and without any hand waving, unlike the proof with by completing the square, we see that x naught, y naught must be a saddle point. We also get a bonus conclusion from this. The period of the cosine graph is pi, 2 pi over 2. Because the period is pi, that means the angle difference between the highest high point and the lowest low point must be half the period, or pi over 2. In other words, the directions of maximal upward and downward concavity must differ by pi over 2 radians or 90 degrees. Stated another way, if we take a look at that Pringles again, the directions of maximal upward concavity and maximal downward concavity must differ by 90 degrees. They must be perpendicular. We can make a similar argument for case 1. At a local extrema where AC minus b squared is greater than 0, the directions of maximal and minimal concavity again differ by 90 degrees. And we can actually make a similar conclusion for case 3, the ambiguous case. In case 3 for the picture, the maximal concavity is positive, but the minimal concavity is 0. I have 0 concavity at the saddle point. Unfortunately, the geometric interpretation is less obvious for case 3. We conclude that for a saddle point with b squared minus AC is less than 0, the direction of maximal upward and maximal downward concavity are orthogonal. The technique of the proof does not require linear algebra and only requires calculus 3 and also some ideas from trigonometry. And we can make a similar conclusion for local mins and local maxes under case 1. I conclude by saying that the usual proof of this requires a significant amount of linear algebra, including the fact that for a real symmetric matrix like the Hessian, eigenvectors corresponding to different eigenvalues must be orthogonal. However, we can logically connect these two different approaches if we were to directly compute the eigenvectors that correspond to the maximal and minimal directions, phi over 2 and phi plus pi over 2. I'm not going to do this here for the sake of time, but if we were to compute those vectors corresponding to those directions, those vectors turn out to be eigenvectors that correspond to the Hessian matrix. Thank you for attending my talk.